Hi everyone, I'm Chen, so I will give my presentation for the title, The Taxation Perspective for Fair Ranking. And so this paper is done by University of China. It's also collaborated with National University of Singapore and Chinese Academy of Science. Okay. So firstly, I will introduce our motivation. So actually, we can see there are IR systems, so users actually drive in a IR system and they will give a query, and the IR model will actually give a ranking list to users according to their queries. So the ranking list often consists of different items, different documents, and just a ranking list. So, but actually previous work found that nowadays the ranking system actually will show extremely unfair exposure opportunities. For example, in the bar, and we can see some items has few exposures, and some items has very large exposure opportunities, and they will dominate the market. And the exposure opportunities are actually very different to different items. And what will cause, and it actually may cause some massive effect. It means the richer items means has larger exposures will have more exposures, and the small items they will made to quit the platform because they has less and less opportunity to be exposed. Okay, so actually the fair ranking actually works. So fair ranking actually the techniques aim to redistribute the ranking slots among the items fairly. So for example, in this graph, and we can see the clothes has very large exposures, and we should to decrease the exposure opportunities and to compensate the lowest item, for example, the towel and the wallet, right? So actually, but we cannot make every item share the same exposures because we also aim to preserve the user's preference, the user's utility. So actually, we need to trade off such the user preference and the item fairness. So actually, the fair ranking aims to trade off those accuracy and fairness. Okay, so actually, the fair ranking, we can regard it as a resource allocation problem because we can regard the users as players and the ranking slots as resources. For example, there are 10 users and 10 rankings. Each user will receive 10 items, and there will be 10 times 10 equals to 100 ranking slots, and this is a limited resource. Okay, so actually the resource redistribution problem in economics is actually through the taxation. Okay, so taxation process is very similar with the fair rankings. For example, in the right figure, and it is federal tax in US in 2016, and they tax the money from the highest quintile people and to compensate the money to the second lowest quintile people. And the tax is going to redistribute the social wealth, but it cannot to make the every person has the same money, right? Because we also need to make the overall society of overall wealth to increase. So actually, it is a very similar pattern with the fair ranking. So we can regard the fair ranking through the taxation process. So why should we reviewing the fair ranking as a taxation process? There are two reasons. The first reason is we can re-examine the previous fair ranking methods, and it's a new perspective. And another is it can inspire to design a new fair ranking methods, and that's the way we propose a new method. Okay, so next I will introduce a specific taxation perspective for fair ranking. So let me introduce some notation first. For example, there are the users, items, and arrives. The ranking system will give a ranking list to the users with a size k. And here we need to define the utility of item because, for example, we can precisely measure the wealth of the person and the money, but for the items in the ranking system, we need to measure the utility of such items. And here we define it is the accumulated utilities. And it counts, for example, here is the Vi equals to the every user's W multiply the X. So X equals to, it's a binary variable. So it's equals to 1, it means item I is exposure to user, and it's actually in the ranking list. And it's to 0, it's not in the ranking list. The WI means there are multiple meanings and depending on the task formulation. For example, WI is to 1, it means we care about the item exposure. When item exposure, big exposure, the utility will count 1, and maybe there are the CTR means if the item being clicked, and it will count the corresponding value. So the value is calculated with the click model or other models. Okay. So it is a and it's pre-calculated. It's not calculated from our model. It's calculated from the other models. Actually, the fair ranking has 2 goals. So one is we need to maximize the overall utility. The platform needs to maximize the profit, right? And another is the platform will aim to ensure the even item utilities as much as possible. So every utility Vi equals to Vg. Okay. So actually, we can see the previous fair ranking can be divided into 2 types. One is regularized method and is a constraint-based optimization method. And optimization constraint means we add a regularizer to the loss function, and the constraint means we aim to the fairness function to not exceed to a certain value. So our V here can be any fairness loss function. Okay. So our paper theoretically prove that the previous ranking method can be viewed as the item level taxation process. Item means that the previous ranking score is gamma I multiply the W, but for the 2 kinds of method, it actually will tax a specific item level taxation. It means the mu I here. So if you're interested in the detailed proof process, you can see my paper. And here is just to know the mu is the item level taxation value, and lambda here is the taxation rate. And we can see that such item level taxation process actually violates 2 important taxation property. One is the continuity. It means that slightly variation in tax ratio will lead to, should lead to minor shifts in performance. But actually, we can say previous method actually, if we increase the taxation rate, it actually has several breakpoints. Maybe it will cause small accuracy, but it also can cause very large ranking accuracy, and it's not convenient for the platform to adjust the taxation rate because it has very many breakpoints. And another is we need to controllability over the accuracy loss. For example, if we increase the taxation rate from, for example, from 0 to 20%, and we should know how much accuracy will we lose. And it is important for the platform to decide what specific taxation rate they will decide, right? Because they will, according to such laws, to decide the policy. But actually, we prove that the previous method actually, this problem is an NP-hard problem, and we cannot solve it very efficiently. And to build on this, we inspire us to design a new model is tax rank. So tax rank is not based on the item level utility. It means the utility between 2 items. Okay, so the loss function is acts like this way. And the detailed proof also comes in my paper. And the taxation rate is not based on the single item. It's based on the utility, the gap between 2 items. So t equals to 0, it will reduce to the accuracy first objective. And the t approaches to infinity, and reduce to the fairness first objective. Okay, so I will give some geometric explanation for this objective function. So here the green area is a feasible region for the ranking. So it cannot, it must fall in the green region. And when t equals to 0, it means do not consider fairness. So actually it is a strict line, it's tangent to the grid region. But if we increase the taxation, if we care about much fairness, and we can see the line will actually curve, the curve will to tangent to the green region, so the red point will approach to the yellow point. And if we continue to increase the importance of fairness, and we can see the line will curve like this, and it will ensure the extremely even the ranking result. Okay, so here we actually also proved our objective obeys the strict continuity, and the controllability of accuracy loss can also be bounded as such bound. Yeah, so I will not go into detail. So okay, so finally is our algorithm. So I will not go to detail, yeah, because of time limitation. So here is briefly introduced. There are two stages. One is the lower bound function. So we can say the previous object function is how to optimize is binary optimization. So we construct a lower bound function, and it's easy to optimize. And secondly, we will to utilize the optimal transportation projection method to project the method into the feasible region, because the ranking solution, it will precisely ensure that each user will receive at exactly k items. So that is a constraint. So we will project such the first solution into the feasible solution. So here is the overall algorithm. It's a very efficient algorithm. So finally, it's an experiment. And here we utilize two data sets. One is Yelp, another is IPU. First is the recommendation data set, another is advertising. The two are also ranking tasks. So we actually evaluate two metrics. One is accuracy, another is fairness. Here our method shows, so our method can Pareto dominate the baselines. So it means if we keep the same fairness metric, and our method can achieve a better accuracy performance. And if we compared to other baselines with the same accuracy level, and our method can achieve better fairness performance. Okay. So another is analysis experiment. So we can see our method can be better controllable over the accuracy loss. The previous method, they can show very strange curve, but our method show very smooth curve, and we can precisely predict the curve, and our accuracy loss is also lower than previous methods. Okay, so next is the better efficiency. So our method has very low inference. If we increase the user size, maybe hundreds, thousands, and our method can maintain very low inference time. Our method is very efficient, but as for the other algorithm, they increase at a linear exponential rate. So, okay. And finally is the visualization. And we can visualize our ranking slots based on the different taxation. So as t is equal to 0, we can see we firstly care about the accuracy, and they will show some very high exposure items that will dominate the market. And if we move to t equals the taxation rate, it will be more fair, and t equal to 3, and it will become extreme. All the item utility will become the same. Okay. So final is the conclusion and the takeaway message. So here we recapitalize the fair ranking tasks as a taxation process from an economic view. And next, we re-examine existing taxation policy, and we can regard it as an item-level taxation policy. And secondly, we just propose tax rank with the item pair taxation policy rather than the item-level policy. And finally, experiment actually show tax rank outperform and Pareto dominates the existing baselines. Okay, so thank you. I'm open to the questions.